Hello, today we're going to be talking about entropy. Entropy is the driving force behind the universe, but it's also going to lead to the end of everything. Now you're probably wondering, what is entropy? Well, there's two different kinds of entropy we're going to cover in this video. Energetic entropy and configurational entropy. I'm afraid we're going to be dealing with a lot of analogies here, so just bear with me. First thing we're doing is balls and cups for energetic entropy. In this example, the balls represent the energy of a particle, and the cups represent the particles themselves. Now, in the example I've shown on screen, we have 3 cups with 2 balls between them. There are 2 different ways this setup can be configured. You can either have 2 balls in 1 cup, or 2 cups with 1 ball. Now, the way we would increase the entropy of this system is by adding additional balls, because that increases the number of configurations we can have. We can have 3 cups with 1 ball, we can have 1 cup with 2, 1 cup with 1, and 1 cup with none, or we can have 1 cup with 3. This is a greater number of states, and so it's an increase in the entropy of the system. Our next analogy comes from the world of Magnus Carlsen and Hans Niemann. That's right, I'm talking about chess. Now, in the first set of examples you can see I've shown, there are 64 possible configurations where these chessboards can be set out. In the first case, that's because we have 1 piece, and in the second case, that's because we have 63 pieces, leaving it only being 1 empty space. In this example, the chessboard itself represents open space, and the pieces represent individual atoms. As you know, atoms can't overlap. This limits the number of configurations we can have. To increase the configurational entropy, you must look at the second set of chessboards that I've laid out. In one, there are 62 pieces on the board, and so there's 2 empty spaces. In the other, there are 2 pieces on an otherwise empty board. In both of these, there are 4,032 configurations. This means it has a higher entropy overall, as is a greater number of configurations. In real-world terms, this means the closer substances are to filling up 50% of the possible space that they can fill, the higher the entropy they have. Increasing the concentration beyond this point limits the amount of spaces the substances can move into, as there's a greater number of substance. Reducing it limits the amount of substance that can move into these spaces, again, reducing the entropy because it reduces the number of configurations. If we wanted to put this into words using the simplified examples we have, we would say that entropy is the state of disorder of a system, and it can be numerically quantified, although we'll get onto that next video. Entropy is referenced by the second and third laws of thermodynamics. They're very important to both. And it's also a component of the Gibbs free energy equation, which is very important when you're calculating how much energy can actually be used but in a chemical reaction. Now, entropy does have some rules regarding how you use it and talk about it. It's referenced in the second law of thermodynamics, as I said, and that law states that while you can decrease the entropy of a given system, for example, freezing an ice cube to decrease its energetic entropy, the total amount of universe can only increase. Because the energy in that ice cube is going to go out into the world and it's going to increase the energetic entropy of some other system to a greater extent than the amount you decreased it in the ice cube itself. Moving on from the second law, we have, obviously, the third law of thermodynamics. The entropy of a perfect crystal at absolute zero is 0. That's pretty self-explanatory. In a perfect crystal, it can't move to form any other configurations. It's a maximum possible density for that substance. And if it's at absolute 0, none of the particles have any energy with which to move, or to share with others, leading to the energetic entropy and the configurational entropy both being 0. As a rule of thumb, if a reaction or observed interaction, such as dissolving, occurs, the entropy of the product is greater than the entropy of the reactants. This is because of the aforementioned law, the second law of thermodynamics, that the entropy of the universe doesn't decrease. For example, when you dissolve an ionic solid in water, the water molecules all moving around the ionic substance and forming ion dipole interactions with it might seem very ordered. It might seem like it decreases the configurational entropy of those water molecules. And while that's true, and it does, it's vast difference from the extremely low entropy of the ions in their ionic lattice state. So overall, the entropy of the system has still increased from that water and ion state it was originally in. Thank you all so much for watching, and stay tuned, for my next video will be on Gibbs free energy.